Welcome to this video. I will introduce how to design a notch filter in the Matlab and use the designed notch filter to test an example case. Here is the question. An input sine signal is composed of 50 Hz and 100 Hz signals. 50 Hz is an interference signal. A 50 Hz notch filter must be designed with a sampling frequency of 400 Hz. According to this question, we should design the notch filter first. Then use the notch filter to work on the input signal to filter the 50 Hz part. Finally, just keep the signal with the frequency 100 Hz. Since the sample frequency fs equals 400 and the continuous time notch frequency is 50 Hz, which one should be filtered later? So the DT notch frequency will be 2 pi times CT notch frequency divided by fs. This is the DT notch frequency. According to the DT notch frequency, we could get the zeros and poles in the Z-plane to design the notch filter. In the Z-plane, zeros equal exponential plus minus j times DT notch frequency, and the poles equal coefficient r times exponential plus minus j times DT notch frequency. Here the r is the radius of the IIR poles. The range of r is from 0 to 1. After we get the roots value, notch zeros, and notch poles, we could use Pauli function to get the coefficients from the roots. For the r value, we could set a value 0.7. Later, we could do some changes. To get the coefficients from roots, we could get b equal Pauli function, notch zeros, and a equal Pauli function, notch poles. After we get the coefficients, we could get the transformation function, and we could use the frequency bottom line m function to get the relative magnitude in dB, absolute magnitude, phase response, group delay. This function I downloaded from the GitHub. It's a general function. I will attach it in the description. You also could use it in the future. After we get these parameters, we could plot the transformation function to check the notch filter in the frequency domain. Figure plot omega times fs divided by 2 pi. The y-axis is dB. X label is frequency in Hertz. Y label is dB, and the title is notch filter response. Let's run it to take a look about the notch filter. We can see the result. When the frequency is less than 50 Hz, it's pulse. The dB is 0, which could pass signal. And when the frequency is greater than 50 Hz, the dB is also 0. It could pass the signal. Just when the frequency is equal 50 Hz, the dB is very low, around negative 300 dB. It will filter the 50 Hz. After we get the logic filter, we could use it to process the input signal. Then compare the input signal with the output signal to check if the 50 Hz signal is filtered by the logic filter. The input signal is composed of 50 Hz and 100 Hz signals, so the expression will be x equal sine 2 pi times 50t plus sine 2 pi times 100t. The first signal is 50 Hz and the second signal is 100 Hz. The t value should have a range. It's from 0 to, and the steps will be 1 divided by fs and to go to 1. Since it's a digital signals, we could plot the input signal first. This one is for original waveform in the time domain. Since here there are a lot of plots, so we could add the subplot. This one we could give it 2 to 1. The second plot here will be 2 to 2. We also could check the input signal spectrum in the frequency domain, so we need to use the FFT to do the transformation. Capital X equal FFT X in time domain. When we plot the FFT, we could use the absolute value. So here we could define M equal ABS capital X. Since in the time domain it's T and in the frequency domain it's F, so we need to define the F vector to plot the input signal spectrum. The F will be from the 0 to length x, capital X minus 1 times fs divided by the length x. So f is the frequency vector in the frequency domain. We could subplot it. Subplot 2 to 3. Plot f m. F is the x-axis and m is the y-axis. And the x label will be frequency in Hertz. Y label will be FFT of original signal. And the title will be spectrum for original. Let's run it to take a look. We can see the first one is the logic filter response, and the second one is the original waveform in the time domain. And the third one is the spectrum for original signal in the frequency domain. We can see that there are two frequencies. The first one is 50 Hz and the second one is 100 Hz. After we pass the logic filter, we just want to keep the 100 signals and filter the 50 Hz signal. Next, we should discuss about the output signal. Y will equal, we could use the filter function, B and A parameters, and the input signal is X. Just this sentence, we could get the output signal, combine the input signal with the filter. BA just the filter parameters. So here we could add a comment, output signal. after filter. For the output signal, we could check the spectrum to take a look if the 50 Hz has already been filtered. We could define x1 equal FFTY, and the M1 is absolute value x1. It's similar, the frequency vector will be from the 0 to length x1, so they are all similar. We just could copy and paste them here and change the name. And the subplot will be 224. Plot F1, M1, and change the Y label FFT output signal. And the title is spectrum after filter. Let's run it again. Now we get 4 plots. Can you see the last one, spectrum after filter? It just has 100 Hz, and the 50 Hz is filtered, which means it works. We also could take a look about the output signal in the time domain. We could give another figure, plot Y in the time domain, and the title should be output waveform. Let's run it. There are 2 figures. The second one, the figure 2, should be the output signal. You can see it's different from the original waveform. It just has 100 Hz signal. Which means the notch filter works. So here is the total project about the notch filter with the input signal and the output signal. I hope you could enjoy this video. If this video helps you, please give me a like and leave a comment. If possible, please subscribe my channel. Thanks for your watching.